Let's start. I have your tests. I already posted them last night, so you may have noticed that they got posted. And I've also updated the flux. I'm going to let you pass these out for me, Yasmin, would you? I also updated so there'll be, obviously, people are going to be coming in, so. I updated your flux, so your flux is updated, except I didn't put in the tutoring for last week. I have that, but I haven't added those couple of dollars. But the flux is essentially correct. So so your average is pretty much up to date, right? With currently. There's no need for a makeup on this test. The scores, for the most part, were okay, so that's good. There are some of you who could benefit from improving your homework score. So you are maybe hovering there close to a C, maybe between a C and a D, and your homework score is low. So that shouldn't be the case, all right? Your homework score should be high, definitely should be higher than your class average. So, therefore it would raise your class average, right? So if you are teetering there on the brink of a C, and you want to do something to, guarantee that you'll make a C and not a D, then you need to increase your homework score, all right? So we don't have a huge number of opportunities left to increase your homework score. We have some homeworks left, though. Obviously, we're not at the end of the semester, so you do have some opportunities, starting with tonight, right, okay, and finishing that integration by parts homework, okay, that's due. And then we're going to talk about trig substitution today. We started it last time before the test, but we'll talk more about that. So I don't know if this due date will, maybe that trig substitution. That's a challenging homework, though, okay? So that one's going to take some time. That is really one where I think Yasmin can help you. Have you talked about trig substitution, Yasmin, in the SI period yet? Okay, yeah. All right, so they're going to need some help on that trig substitution homework. Y'all may think about working on the homework problems together during the SI period, because some of them are really tough, and are going to the Math Center to help you with your trig substitution homework. That's one that is going to be difficult to get a really high score on, because the problems are hard. But partial fractions would be a little bit easier in L'Hopital's rule. So you still have opportunities to improve your homework score, and then that will improve your average, as I mentioned. Okay. All right. So that was the main thing I wanted to point out. Okay. The answers are posted. The answers are posted on the Blackboard page as usual. So I put those up this morning. So those are Yasmin's answers, and which are very good. So you can look at the correct answers and compare those to what you put on the test, right? But it would really behoove you to try to correct the test first, correct your mistakes first, before you look at the test answers, all right? So, but if there's something that you just cannot fix, all right, then you just don't know what to do, then of course look at the test answers, right? But try correcting it first on your own, so that you will remember it for possibly the final exam. Also, now remember that some of you, okay, have now collected pretty high calculus flux totals, and so you are within easy striking distance of buying out of the final exam. So to make, if that's an incentive for you, you don't want to take the final exam, then keep that in mind. So look at your flux total. How many dollars do you need to buy out of the final exam? Is it 75? 75, okay. So, and some of y'all are close to 75 already, so a good score on a reasonable score on test number 3, and then maintaining your attendance, and then keeping your homework average up, right? There's that homework average again. Will easily put you over the threshold for buying out on the final exam. Some of you, all right? So be thinking about that, right? Okay, and maybe that will motivate you to finish out the semester here strong. All right. Okay. Are there any questions so far? I mean, I know you probably have questions on your test. Like you defer those. What? Oh, on the homework. Okay. Yeah. Is that the secant problem? Wow, that's a good question. I'm not sure. Okay. Did you try? Which one is it? Near the end, I thought you were going to ask me number 9. This one? Yeah. Okay. I thought you were going to ask me. Where's the one? Oh, okay. All right. These two, which are very similar, it looks like. Okay. Okay. So y'all tell me what you did on number 9, and so tell me what you tried, okay? Because as I kind of stressed here, right, integration by parts is kind of trial and error, right? And so if you tried something and you didn't like what happened, then you may have tried something else and didn't like what happened there either, right? Okay. But let's see what happened to those attempts and see if we can complete some of those. Attempts. I was going to show you as an example, though, this problem, which might be similar, but this one is tough. Okay. I think that's tougher than that homework problem, but it might be similar in some respects. All right. So let's see. What was that problem? The antiderivative of the indefinite integral of e. Was it e to the 9x? So you may have had a slightly different coefficient here times what? Sine of x? Yeah. All right. So what was y'all's basic strategy there? What did y'all try first? Obviously, I think it's integration by parts, right? Okay, so that's the overarching strategy. Although they do point out that not all of these problems require integration by parts, but this one looks like it's going to require integration by parts. I don't see an alternative method for this problem. This looks like it's just perfectly made for integration by parts. Okay, it clearly involves this product, right, of these two functions, and that often is a clue that integration by parts might be helpful. All right. So once you've decided on integration by parts, then of course you just have to decide how you're going to break up that integrand, right? So what is going to be the u and what is going to be the dv, okay? And so remember the general guidelines is given in the book, right, are you want to pick u so that its derivative is simpler than the original function, correct? Okay? And then you've got to pick the dv so it is something that you can integrate, all right? So I guess the obvious choices here, as a trial would be something like, we're going to let u be e to the 9x, right? And then we'll let dv be the rest of this, which is sine x dx. And both of those are sort of useful, okay? Because both of these sort of fit those guidelines, because if you take the derivative of u, right? If you take the derivative of u, then you're going to get 9e to the 9x. Don't forget the chain rule, right? So you get 9e to the 9x. That is slightly more complicated than u, so we've sort of violated that guideline that we want the derivative of u to be easier than u, but it's not horribly worse than u, right? Okay, so it's about the same as u, and dv is easy to integrate, right? It is easy to integrate sine of x because that will integrate as, I think, minus the cosine of x, correct? Okay, so so you can integrate dv there, okay? If you switch this around, that also would be okay. So we could also let u be sine of x, right? And then we could let dv be e to the 9x dx. And I think that would also sort of be okay because the derivative of u would be just, of course, cosine of x, right? That's one of our favorite derivatives. And we can integrate e to the 9x, okay? That's not difficult to integrate. So you may have to use a little bit of substitution there, right, for 9x, but you can integrate e to the 9x. So that seems like that also would be suitable as a way to break apart the integrand, okay? Maybe either one will work. What did y'all try? Did someone try something here? You tried this one? Okay. And did other people try this one? Yeah. Well, no, so why? Why did y'all pick this one? Oh, they have an example like this?
Yeah, I tried to look it up.
Oh, okay.
I tried to work it out like before watching the example, and I was just glad that they used the same method, but I think I finished watching the example all the way to see how they got back to
Okay.
get the same thing. I didn't quite understand that.
Oh, okay. All right. Justin, were you going to raise your hand? You what? What? How? What now? You know how to solve it? Okay. Do you use the second substitution?
Yes.
Okay. All right. So So if I mess up here, then Justin will help us. Okay. Because he says he got through it. All right. So let's see. Does this fit the does the Lie guideline match this way of breaking up the integrand? Sahai, is that what you're thinking? Why? Because trigonometric? Yeah, that's right. So in Lie it would be, you're going to let u be the logarithmic, not here, right? Inverse trig function, not here. Algebraic. Neither one of these functions are algebraic. And then trig, right? And so there's your trig function, right, in your integrand. So the Lie also suggests let u be sine of x, okay? All right, so let's try this one. All right, so so we have to integrate now dv, right? So we've got to integrate dv to recover v. So we want the integral of e to the 9x. Do I need to write down the full substitution here? Because I have to be careful if I do that, because I don't want to reuse u. Let me do it without actually writing down the formal substitution. In order to integrate e to the 9x, right? That would normally integrate as just e to the 9x, right? Correct? Normally you integrate it when you integrate an exponential function, you just get the exponential function back again, right? Except the complication here is that the exponent here is not just x. The exponent is 9 of x, right? So in order to integrate this easily, you're going to need the derivative of 9 of x multiplied into the integrand. But of course, what is the derivative of 9 of x? 9 times x, I mean. It's just 9, right? So I'd like to have a coefficient of 9 here to make this easy to integrate. Everyone understand that, right? Okay? I really need coefficient of 9 here to make that easy to integrate. So I'm just going to put the 9 in there. But to compensate for adding that 9, correct, I need to fix that by multiplying by 1/9. So outside, I'm going to multiply by 1/9. Okay? So here you have an exponential function times its derivative. So that's easy to integrate. It's just going to be the exponential function. But the 1/9 shows up now because I had to artificially create that coefficient of 9, right? So when you integrate this, you get, very easy there, 1/9 e to the 9x. See, this 9 is going to disappear, right? Okay, as part of the integration. So there's v. It's 1/9 e to the 9x. All right, so with v and now that we know, we also know du, right? Du is going to be cosine of x dx. Just multiply both sides of this equation by dx, right? And now we're ready to write down our basic integration by parts formula, which says this integrand is going to be u times v, right? So that would be sine of x times the times v, which is 1/9 e to the 9x, right? Minus, and then the antiderivative of v du, right? So v is 1/9 e to the 9x, and then du is cosine of x dx. Nice, all right? So I have here 1/9 sine of x times e to the 9x. Maybe I should have written the e to the, let me write that in a different order. Let me write the 1/9 e to the 9x in front. So 1/9 e to the 9x sine of x minus, I'm going to pull this 1/9 out. So now I have 1/9 times the integral of e to the 9x cosine of x dx. So ignore all of this. So, well, okay, that's a little bit disappointing, right? But not completely. Because I seem to have arrived back at a very similar problem, right? Now I have e to the 9x times cosine of x instead of e to the 9x times sine of x, all right? So at that point, you might start to panic a little bit, okay, and think that you're going in circles. And that might lead you back to trying this way of breaking up the integrand. But you shouldn't quit too soon, okay? So what we're going to do here is actually apply the integration by parts formula again, all right? So I'm going to do iterative integration by parts, all right? I'm going to do it a second time on this integral, okay? So this part is fixed. Now I'm going to try integration by parts again on this one, breaking up the integral in exactly the same way I did before. So I'm going to let u be cosine of x, and I'm going to let v be e to the 9x dx. I mean dv be that, all right? So here's my second go around with integration by parts. Pardon me, I'm still coughing a little bit. All right, so let's see. We're going to let u now be cosine of x, right? So du dx is, what, minus the sine of x, right? Which means that du is going to be minus the sine of x dx. And then v is going to be, again, the integral of e to the 9x, right? Except this time, well, no, not this time, right? We get exactly the same thing for v, which is 1/9 e to the 9x. Because I already did that same integral a moment ago, right? With my first version of v, right? My second version of v is going to be exactly the same. So we'll get, again, 1/9 e to the 9x. All right, now let's plug those in to this equation. Now be really careful, right? Because you've got a lot of things going on now in this expression. All right, you've got this left over from the original time you applied integration by parts. So you have 1/9 e to the 9x sine of x minus 1/9 times, and then you're going to apply your integration by parts formula to that e to the 9x cosine of x, right? So leave the 1/9 out of it, all right? The 1/9 is right here, and so that's why I'm putting the brackets. You could, don't have to use brackets, you can use parentheses, right? Now I'm going to apply that integration by parts formula a second time, okay? So I will get, what will I get now the second time? Well, it's u times v, right? So we'll get 1/9 e to the 9x. That's the v. And then the u here is cosine of x, right? So times cosine of x. And then minus, and what goes after that minus sign now? It's this, right? Okay? It's v times du, which is minus the sine of x, okay? So I get minus integral, can I squeeze all that in there now? 1/9 e to the 9x, and then minus sine of x, because that is du, right? Dx. So let's see what happens here. These are going to cancel, right? Okay, so those are going to cancel, and so I'm going to get plus there. I can factor out this 1/9 as well. Okay, got a lot of 1/9 here. So 1/9 e to the 9x sine of x minus 1/9 here, and then 1/9 e to the 9x cosine of x plus 1/9, and then that's plus now because these two minus signs canceled, right? And then integral e to the 9x sine x dx. Okay, Daniel, is this where you stopped? Okay. You didn't know what to do at this point? Okay. All right. This is, all right. So, yeah, so I think the first reaction would be to kind of freak out, right? Okay. Because you seem to be going in circles, right? Okay. Here we are back with another integral that involves exponential function and a trig function, right, Duck? Okay. So, in a sense, we are going in circle, but this circle is actually fortuitous for us, all right? We're going in just the right type of circle, okay? Because now what has appeared again is the original integral that we were trying to find, right? Okay, so we're back to integrating e to the 9x sine of x. Remember, all of this is equal to that integral, correct? Right? All of this is equal to this. Let's rewrite that. Just pull this down. So all of this is equal to integral e to the 9x sine x dx. That actually means now that you're going to be able to solve the problem, okay? Here's why. Because I'm going to gather these two integrals on the same side of the equation, okay? All right? And they will add together because they're like integrals, okay? It's kind of like adding like terms together, all right? And then I'm going to leave everything else on the other side of the equation. Now, I have to be careful when I do that. Arithmetic, though. So I have 1/9 this, and then this minus 1/9 is going to distribute, right? So I'm going to get minus 1 over 81 here, right? Okay, so minus 1 over 81, and then this will be also minus 1 over 81 times this integral. So actually, let me distribute that. Let me distribute that minus 1. So I'm going to erase this again, but I'll write it again in just a second. So I have 1/9 e to the 9x sine x minus 1 over 81 e to the 9x cosine x minus 1 over 81 times this integral, e to the 9x sine x dx. And all of that was supposed to be equal to integral e to the 9x sine x, because that's what I started with in the original problem. So think of this as one equation, this equal to this. So what you can do now is take this term and pull it back to this side. Okay. So those two integrals will add together. How many of those integrals will you have then?
Wait, would it be minus 181? Wasn't it positive?
Yeah, this one's positive, but this one's minus, right? So when I distribute it, these two become minus, correct? Okay. All right. So when you pull this back to this side, how many of these integrals do you have? Well, you have one of them here, and you're adding what? 1 over 81 of them. So how many does that give you altogether? Yeah, you said it there. What? That's right. So you have. So I'm starting. I'm going to start a new equation now. So I now have 82 over 81. Okay, of these integrals, e to the 9x sine x dx, and that's equal to all of this that's left here. All right, which was 1/9 e to the 9x sine x minus 1 over 81 e to the 9x cosine of x. Cosine of x. Because that's these two. I brought this over and added it to this, and then these two things were left over. So did I write that down right? 1/9 e to the 9x sine x minus 1 over minus 1 over 81 e to the 9x cosine of x. Okay. Now you're done. Okay. You're done, because now you can just solve this equation for this integral, which is easy to do. All you have to multiply is by what? 81 over 82, both sides? Yeah, just multiply both sides by 81 over 82, the reciprocal here. Okay. So let's do that. So you multiply this side by 81 over 82, and multiply this side by 81 over 82. Because I had one of these and 1 over 81 of these. Same thing, right? So I added this one to this one. So when you have 1 and you add 1 over 81, that gives you 82 over 81 of those things, right?
Because you're using the algebraic properties, if it's a negative integral, it'll be a positive integral to bring over to the other side. Is that how you
Yeah, that's just algebra, right? I have a negative term on this side, so when I pull it to this side of the equation, it becomes positive, correct? Okay. Remember that series of equations. This is now a different equation. So but the original series of equations was you started with this, equal, right? Okay? So what you had is this is equal to all of this. That is your equation, right? You've got this equal to this, because that's what we started with. I just rewrote that down here, okay? Just so you could see it again. So you got all of this is equal to this. So I'm going to take this and pull it over to this side of the equation. Okay? So that gives me this new equation where I have 82 over 81 of these things is equal to what's left on this side of the equation. Okay? And now I just multiply both sides, as I mentioned there, by 81 over 82. So you get, there's your finish now. E to the 9x sine of x dx is equal to, well, let's see. When you multiply 81 over 82 times this 1/9, I think you get 9 over 82, right? Because 9 will go into 81. And then same thing here. Oh, no, that's even better, right? The 81s will cancel, so you get minus 1 over 82, e to the 9x cosine x. Cool. All right. You know you can actually check that. This is the great thing by when you find just indefinite integrals, right? You can always check your answers. So you can just check this, okay? Just by taking the derivative of this, taking the derivative of the right-hand side there, and see if you come up with e to the 9x sine x, right? Okay? Because that's what this is supposed to be, right? This is the antiderivative, right? So when you take the derivative of this, you should come back with e to the 9x sine x. That's going to be kind of a formidable differentiation problem because you're going to have the product rule twice. You have the product rule here, and you'll have the product rule here, okay? Well, let's see. Oh, I forgot the constant. All right, so add that on at the very end. That has to be there just as, because this is an indefinite integral. That one terrible?
It's just really long.
It's long. Yeah, I kept warning you. These problems are really long. Wait till you do trig substitution. Those problems are going to be really long as well. Okay?
How do you know that when you've taken it as far as you can? Because with some problems, they're a little bit easier, but then does he think that it's...
Yeah, this is just, I think just having seen an example and then realize when the, here when the original integral reappears, right?
Okay.
When the original integral that you were trying to find reappears, use that is good. That's good. Okay, something good has happened. All right. Okay, that's recursion. So when you do integration by parts twice, that's iterating. Okay. And then when the original problem reappears, that's called recursion for those computer scientists, right? So, when that recursion appears, that's good too, okay? Because then you can pull this trick of shifting, shifting that the original integral, right, back to the other side of the equation, and then solving. We're going to see another example of that just now, actually. All right. So it looks like problem 10. This was problem 9, right? So it looks like problem 10 is going to be somewhat similar. So you get a chance to practice that again in the homework. Doc, are you okay with that? All right. Okay. All right. Let me show you another example now. This one's actually trickier. This one's not at all straightforward, but it does involve recursion. But it's not one that you would. This is one that is not one you would. You'd have a difficult time solving this one if you're just giving this as a straightforward problem on a homework. Okay. All right. This is finding the antiderivative of secant cubed. All right. So we're going to use integration by parts. So it doesn't at all appear obvious how to use integration by parts on this problem. Okay. But so this is really the key trick. What we're going to do is break this up. This secant cubed, I'm going to break that up as secant times secant squared. Okay, I'm going to break it up as secant times secant squared. So if you don't see to do that, then you're kind of this problem is kind of hopeless. Let me copy this somewhere where Maybe I have some room. All right, maybe this is enough room. All right, so so again, to do this, I'm going to rewrite this as secant of x times secant squared of x dx. And that's exactly right, because I know how to integrate secant squared. Okay, how do you integrate secant squared? What's the what? Oh no. Shall we write that down? Yeah, how can we integrate that? I claim it's easy. Yeah, it's just tangent of x, right? Okay, that's just tangent of x. And why do you know that? Because the derivative of tangent is secant squared, right? Okay, so you have to, just apply your knowledge of trig derivatives, okay, to recognize, oh yeah, I can integrate secant squared because I just happen to know that the derivative of tangent is secant squared. All right, okay, so that's what makes that one easy. You were trying to apply the anti-power rule, okay, and integrate that as secant cubed x over 3. But you cannot use the anti-power rule there, Fred. Why not?
Because it doesn't apply because it's a trig.
No. You can use the anti-power rule on anything, all right. But what was the condition that was not met there to apply the anti-power rule? So why can we not integrate this as secant cubed? So why is this not equal to secant cubed x over 3? Why not just add 1 to the exponent and divide by the new exponent? Yes, because secant x is a function, right? It's not just x squared. It's secant of x squared, okay? And so to use the anti-power rule, what are you going to need there? The derivative of secant. You're going to need the derivative of secant multiplied in. What is the derivative of secant? It's secant times tangent, right, okay? So you would need secant times tangent multiplied in here, okay? You would need secant times tangent multiplied in, all right? But you don't have, you just have secant squared, right? You don't have secant times tangent multiplied in, all right? So you cannot use the anti-power rule, right? You cannot use the anti-power rule. But that's great. We don't need the anti-power rule because this is easy to integrate anyway, right, okay? It just integrates as tangent of x, all right? So this, I guess, is our dv, right? So, I'm sorry, that's our v. That's going to be our v, right? So that means that, because we integrated this, so that means dv must have been this, correct? All right, so that was my choice for dv, and so that just means that secant x is my choice for u. Now that kind of violates the guidelines because when you take the derivative of u, it's not simpler than u. Okay, what is the derivative? We just mentioned it there. What is the derivative of secant x? Yeah, secant times tangent, right? So it's secant x tangent x, which is not easier than u, right? Okay. But nevertheless, I'm going to go with that. So, see, the guidelines are not foolproof. All right. Okay, so now let's write down the our integration by parts. So this is going to be u times v, so that's secant x tangent x, right? U times v minus the integral of v, which is tangent of x, right? Times du, which is secant x tangent x. And then we have kind of a seeking feeling, right? Because that looks now really bad. So it looks like I have not made any progress here. I can rewrite this, though, as secant x tan squared x, right? Tan squared x. Well, here's what I gained. Tan squared x, okay, that is part of one of our Pythagorean identities, right? So we talked about these last time, and these are going to be important to us again today. So, well, they're always important, but especially today, starting right now. So sine squared x plus cosine squared of x is equal to 1. That's the most famous Pythagorean identity, you know. But the second one is what? Is it secant squared x minus tangent squared x is equal also to 1? Right, so that's the second Pythagorean identity, and that one involves tangent squared x. So, you know, when you come across tangent squared x, you should be reminded of this Pythagorean identity because it's sometimes very useful, okay? So tangent squared x is really secant squared x minus 1. So I'm going to substitute that here into for tangent squared x, okay? So that I can get everything just involving secant. What now? Now, I think this is minus, isn't it? Well, I'm moving this to this side and this to this side, so the signs change, correct? So I get secant x, tangent x, minus, and now this is secant x times secant squared x minus 1. And it's not clear why that's helpful until I actually distribute the secant squared x. And when you do that, you notice this becomes secant cubed x minus secant x. All of that dx. And these are two terms, so I can break this up into two integrals, right? Two terms in the integrand. So I can break that up into two separate integrals, and I'm going to do that. So I have minus integral secant cubed x dx, and then plus integral secant x dx. And see what has happened? Now the recursion has occurred, okay? That is the original thing that I was trying to integrate, right? So you have to go all the way back up, but that's what we were trying to integrate, right? Into this sequence, this long series of equations, right? So remember, all of this is the integral of secant cubed x dx, right? See, this is the equation. And now we can pull the same trick that we did in the previous problem. So what am I going to do? I'm going to take this, and I'm going to add it to this side of the equation. Because remember, this was equal to all of this, right? So I can pull this over here, and I get two of those. So I don't have to worry about, you know, denominator of 81 and 82, right? So I'm starting a new equation now. So I have 2 integral secant cubed x dx is equal to, let's see, what's left now? Secant x tangent x, right? Minus, no, is it minus? No, it's plus, right? Plus integral secant x dx. So if I just know what the integral of secant x is, if I just remember what the integral of secant x is, then I just have to take all of this and divide by 2, and I will be finished, okay? What is the integral of secant x, though? I bet you've forgotten it, because it's not one you're going to memorize, but you know it, all right? Okay, we have learned that. Yeah, it involves natural log, that's right, okay? So can you all look that up for me? It's not an easy natural log. ln of what? The absolute value of what? Secant x plus tangent x? Whoops. Plus tangent x. Yeah, I don't need the c yet, though, okay? Because we'll save that for later, all right? So this is equal to this, so all you have to do is divide by 2. So we're finished. So secant cubed x dx is equal to, how do you want to do that? With 1/2? Maybe 1/2 is better, right? So 1/2 secant x tangent x plus 1/2 times the natural log of the absolute value of secant x plus tangent x. Cool. Plus a constant. Wow. You've just gotten super smart, okay? No, I'm serious, okay? That's really impressive, all right, to know what the antiderivative of secant cubed of x is, okay? There it is, all right? So we get to apply all sorts of knowledge here of trig, right, okay? This clever little logic trick with recursion, okay, so nice, right? And then our knowledge of natural logs there, right? We know that we can use natural logs, or we learned before that we can use natural logs to integrate secant x as the natural log of secant x plus tangent x. So there's so many things wrapped up in that. Antiderivative. All right. Okay, so that one, again, that's not one that you would probably, on your own, if someone just said, oh, integrate secant cubed of x, okay, it does involve a few tricks, right, okay, recognizing that, yeah, if we write secant cubed x as secant times secant squared, I can use integration by parts, and then realizing that using the Pythagorean identity, right, you can come back up with secant cubed x again, right, okay, so that one you have to see as an example, but that really is a good example. All right, so that's in the notes now, okay? Well, I think that leaves you with just one homework problem, number 10, that may be similar to, that may involve recursion, where the original integral will recur when you apply integration by parts. Okay, I'm going to stop there. All right, well, not to pile on here, okay, but now let's do some problems involving trig substitution, because these also are really challenging. So you've already been doing trig substitution. Actually, you've already been doing trig substitution when we applied these antiderivative formulas, right? These are derived by using this trig substitution technique. These formulas are derived by using this trig substitution technique that we're getting ready to practice right now on some other problems. Okay, so you did these in the test very easily, but it was just a matter of recognizing that the integrand was in a particular form, right, in which you could apply these formulas. So we're going to look at also applying not exactly these formulas, but again, the idea that was used to derive these formulas on some integrands that are maybe a little bit more challenging than the ones on the test. So here are the substitutions that we're going to use, okay, in certain situations, and they're often helpful. So if you have an integrand that it doesn't have to be just this by itself, but if you have an integrand that involves a square root like this one, then we are going to make this substitution into the integrand. Okay, so we're going to make a substitution, but it's not going to be well, it is kind of a U substitution. It's actually kind of a double substitution. But the primary substitution is going to be, we're going to substitute for x. We're going to substitute as the variable. We're going to substitute in an angle theta. Okay, so we're going to change the variable from x to theta. That's going to be our goal. But the integrand has to involve an expression that looks like this. Okay, it doesn't have to be just this expression, but it has to involve an expression that looks like this. So a is a constant here, and u is either a variable, just the variable x, or an expression involving x. So it could be something more complicated than just x. But frequently it will just be x. All right? So notice that you should already be sort of tipped in, right, about sine, okay? Because remember, we used arc sine. What did we use arc sine on? When the integrand looked like, what was it, 1 over square root of a squared minus x squared, right? Is that what's on the test? There's one on the test that involves arc sine, right? Which one is it? The second one? Yeah, it's the second one, right? And notice there you have 1 over the square root of 1, which is 1 squared, minus, and then there you have an expression squared, not just x squared, but you have an expression involving x squared, right? Okay, and you ended up using the arc sine function, okay, to integrate that. In certain cases, though, if you just have this type of expression in your integral, right? So it's square root of, again, constant squared minus x, or some expression involving x squared. Then we're going to substitute in this trig expression, a times sine of theta, for the u, okay? Right? And when we see some examples, you're going to see why that turns out to be useful, why that particular substitution turns out to be useful. All right? So we're going to change the variable here to theta. If you have square root of constant squared plus expression squared, then we're going to substitute in a times tangent of theta, okay? All right? So remember that we did that when we were using arc tangent, right, to find an antiderivative if you had a sum of two squares, correct? Okay? Use arc tangent. Same thing here. You've got sum of two squares. Notice it's under a square root, though. It's got to be under a square root. So under a square root there, you can use arc tangent as, you can use tangent as a substitution. And finally there, it's opposite of this one. If you have expression squared minus constant squared, then we're going to use secant as a substitution. All right? So see the basic idea there? If you recognize square root of difference of two squares, you're going to use substitution involving secant, right? Okay? If you have square root of sum of two squares, you're going to use tangent. This is also difference of two squares, except the constant comes first and the expression comes second. Then you'll use sine of theta as a substitution. And I claim that when you make that substitution, frequently you will simplify the integral. I know you're thinking that's not possible because I'm putting in trig, right? How does that simplify anything? But it will, okay, because sometimes, because trig has a lot of identities we can use, right? Okay, and those identities sometimes turn out to be helpful. Okay, I was trying to Google and find out who actually was the first person to make these substitutions, but I couldn't find that. Okay, it wasn't mentioned. If y'all can find that, let me know. Okay, it may be lost to antiquity who was the first person to made such substitutions, but I doubt it. It's probably known. Okay, some historian of mathematics knows this. All right, let's look at an example. Good example to start with. Okay. Now, remember, in this guide here, right? They're always using the variable u, right? Remember, that is either x or an expression involving x. Okay, so keep that in mind. All right. But this is the actual substitution that we're going to make. Okay. All right, so look at that integrand. Look at that integrand. And you know, the first thing that you would see there is you might think, I want to integrate that using the arcsecant function. I just want to integrate that using the arcsecant function. And so I don't want to worry about doing trig substitution. I just want to use the arcsecant function to integrate this. And that almost fits in to that arcsecant pattern. The arcsecant pattern would say what? You would need what? 1 over, and then you have a square root like this one, right? But what do you have outside of the square root? What? Yeah, just u, or in this case, just x. All right, but you don't have it squared. That's the problem. Okay, so if I just didn't have this square here, is that like on the test? Very similar to the problem on the test, isn't it? What was the problem on the test? Was it 25 minus x squared or something?
X squared minus 25.
What?
X squared minus 25.
Oh, yeah. Okay. I'm thinking of, I got it backwards here, all right? I was thinking of problem B, all right? Yeah, to use secant, you need the x squared minus the constant, right? But here we have it in the opposite order. All right, so secant is not the right choice there anyway, but neither would arcsine work, right? If you just had square root of 9 minus x squared, then you could use arcsine, correct, to integrate this? But the x squared is what's messing that up, okay? So if we just had square root of 9 minus x squared, we could integrate that using arcsine without just one single line, right? Okay? But the x squared is just messes all that up. So I'm just not going to be able to use plain arcsine. That doesn't mean arcsine is not going to show up somewhere in the answer to this problem, okay? The antiderivative to this indefinite integral, but it's not going to show up immediately, all right? Okay, but that's fine, all right, because I still do have square root of 9 minus x squared, and that means I can make a substitution, okay? I can make a substitution according to this table. All right. We just have to identify what's the a and what's the u. All right. And then what the substitution is that I want to make. All right. So what is the u here? What now? Yeah, that's right. U is just x, right? Okay. Because here you just have x squared, so you just have u squared. What's the a? Right. Okay. So see, if you make those substitutions, you would end up here with, something like u squared square root of 3 squared minus u squared, right? And I'm not sure what the dx is because I'm not gonna actually calculate dx here. Well, let's go ahead and do it. So du dx is going to be what? 1 So, so that's nice. So du is just equal to dx, right? So you would have du here instead of dx. And see, there you can see perfectly, right? That perfectly is the correct type of integral, right? That will allow you to make a trig substitution. So what's the trig substitution? You probably didn't get a chance to write those down, but it's what? U is going to be what? A sine theta, right? Okay. What's the A here, though? 3, right? Okay. So we're going to let U here be 3 sine of theta. Okay. Now, look, I don't usually go through this step, okay, of substituting in the U, all right, because that's just, because we're going to immediately now come back and resubstitute for U what? Yeah, we're going to substitute for U 3 sine theta, right? Okay, so to me that kind of adds a little bit of an extra step there. So I usually don't actually write this down. I usually go directly from here to substituting in theta, all right? Okay, so I go from x immediately to theta. And that's pretty easy in this case because, of course, x is the same as what? What did we say x was? No, x is u, right? So, see, what you're really substituting in here is for x, you're substituting in 3 sine theta, right? Okay. Now, what is, so that substitution is pretty easy, right? So I'm going to have integral now here of, let's see, what's x? That's 3 sine theta, right? But I'm squaring it. So you get 3 sine squared theta. And then square root of course, this is 3 squared, right, or 9, minus, and then here you have it again, right? 3 sine theta squared, which is going to be 3 squared times sine squared theta. But you also have to get rid of the dx. You have to get rid of the dx, okay? So, look, because you want to change everything to theta. So take the derivative of x with respect to theta, dx d theta, okay?
Why aren't we squaring the 3 as well outside? Because the whole thing is equal to x. So shouldn't we be like square everything, like 3 sine theta square?
This is going to be, what now?
What is outside?
Oh yeah, I forgot to square this 3. I remembered there, but I forgot to do it here. Well, I should have written that as, let me go ahead and write it properly so we don't, okay, all right. So there's the x squared, right? Okay. What now?
Writing the derivative with respect to theta. Why do we have to replace dx with d theta?
Because I've got to get rid of all of my x's, right? Okay. So I've got to get rid of the x's. All right. So let's take the derivative of x here with respect to theta. All right. Okay. So what's the derivative of 3 sine theta? What now? Is that 3 cosine of theta? So what's dx then? Three cosine theta d theta, right? So that we can also now substitute in, all right? All right, now we want to see what's going to happen here. Looks, at this point, really bad, right? Okay?
Is that 3 cosine theta d theta?
Right, because I took the derivative of x with respect to theta, so that gave me 3 cosine theta, right? That's the derivative of 3 sine theta, and then I just multiplied both sides by d theta, just so I could have it written as dx. All right. So that, what does that look like to you? Something else? That's d theta. Okay. So that's supposed to be a theta right there as well. I'm just not writing my thetas very cleanly. That's supposed to be a theta also. Okay. Now at this point you're thinking this is terrible, right? It looks far worse than what we started with. Okay. Well, that was pretty bad to start with. Okay. But this certainly doesn't look that great. But now this is where maybe the trig is going to help you some. Okay. So let's see what happens here. That's what I'm hoping for anyway. So so this is what? 3 squared sine squared theta. Of course, that's 9. And then underneath the radical, this was the whole point. Underneath the radical, notice you can, this is a 3 squared, correct? So you're going to get 3 squared. I can factor that out of both of these terms. And then I get 1 minus sine squared theta. And that's exactly what I was hoping for. Because what is 1 minus sine squared theta? That's cosine squared theta, right? Okay. And this 3 you can also extract from the square root, okay? Because that's the square root of 3 squared, right? So you can extract that from the square root. So wow, things really are looking up. Might as well write that as 9. So all of this turns out to be just 3 cosine theta, right? And see what happens nicely there? Those cancel each other. Yeah, the d theta gets to stay there. I need that, or I'm not going to be able to integrate, right? Okay. So, and this is a 1/9, which I think I can pull out in front of the integral, right? So I have 1/9, 1 over sine squared theta, d theta. So you can leave the d theta on top, or you can write it over here. But what is 1 over sine squared? Oh, it is, right, isn't it? Okay. So is this 1/9 of the integral of cosecant squared theta, d theta? But now, is that easy to integrate? It's minus cotangent. That's exactly right, right? Okay? Because the derivative of the cotangent is minus the cosecant squared, right? Okay? So that is easy to integrate. So we end up there with minus, wow, I hope I did this right, minus 1/9, what, cotangent of theta plus a constant. Because this we actually can integrate, okay? That integrates as just cotangent, because the derivative of cotangent is minus cosecant squared. So I need to add the minus sign, right, because I don't have a minus sign yet. But now I can integrate that. Okay? But we're not quite through, all right? We are not quite through because the original problem, it was not stated in terms of theta. It was stated in terms of what? X. So I now have to switch back to X, okay? Whoa, I have to how in the world do I switch back to X, okay? All right, now this is where your all that practice, or that little bit of practice you had with drawing right triangles is going to be helpful, okay? So we're going to draw a right triangle here that's going to involve theta. Now, what do I know about theta to start with? I don't know much, but I do know from this equation, x was equal 3 sine theta, right? So that means that sine of theta is equal to what? X over 3. Now, I'm going to put that into this picture because sine in a right triangle is, what is that? Opposite over hypotenuse? Is that right? So let's draw that in here. So the opposite I'm going to draw as x, and the hypotenuse I'm going to draw as 3. What does that mean this side is then? Well, this side squared plus x squared has to be 3 squared, right? So a squared plus x squared, this is a different a now, is equal to 3 squared. So that means that a is what? The square root of, oh, it's this, isn't it? Isn't it this square root right here? 9 minus x squared, right? So this side is the square root of 9 minus x squared. Now, why did I bother to do that? Because now I know how to calculate cotangent. How do you get cotangent of theta? What's cotangent? In a right triangle? Adjacent over opposite, right? So it's this over this. And notice that involves x. Okay? All right, so let me write that down. I'm running out of room here, but let me write that down. So cotangent of theta is square root of 9 minus x squared over x. That's what y'all told me. And so now I can use that right here. So I have minus 1/9 times square root of 9 minus x squared over x, because that was cotangent of theta. And now you're done. So minus the square root of 9 minus x squared over 9x, actually, plus that constant.
But either one of those could still be the correct answer, right?
No, that is the correct answer. Yeah, okay. Because the original problem is involving x, right? Did not involve theta. So your antiderivative has to involve x, right, as the variable. Okay, so is that terrible there? It's long? It's long, yeah. It's not really tedious. because you have all those exciting things that you know that you're utilizing, okay? But it is long, all right? I can't deny that it's long. All right, well, we can't just live with that example, right? So we're going to try another one. All right, so y'all have to help me with this one now, okay? You got to tell me what is the correct substitution, right? First, let's write down U and A, because if we don't have a U, if we don't identify the U and the A, then this is not going to involve trig substitution. All right, so what would be the U and the A, and what would be the correct substitution? The U is 2x, perfect, right? Because 4x squared is U squared, right? If U is 2x. So I want you just to identify that first, right? Because 4x squared is 2x quantity squared, correct? And what's the A? Got to get that one right, okay? Perfect. No, we don't need du. Okay, I'm gonna write down the U and the A, but I'm not really gonna make the U and the A substitution. All right, I just want them there so that for reference, but I'm actually gonna substitute immediately from x to theta. Okay. All right. So, but what is the correct substitution? It's tangent? Yeah, all right. So you're going to let U be what? A times tangent of theta. So 1 times tangent of theta, right? But what's U really? 2x, right. Okay. All right, so that's the substitution. I'm going to substitute it for 2x tangent of theta, or you can think of it, I'm going to substitute for x tangent of theta over 2. All right, if you want to. So you can also think of this as x is equal to tangent of theta over 2. If you like. All right, so what is this integral now really equal to when I start making my substitutions? We will, yeah, in just a second, okay? I just wanted to start us with the substitutions. So what's going to happen here? It's just tangent of theta squared, right? Okay, because 2x is tangent of theta, right? So that's 4x squared, which is just 2x quantity squared, right? So you just have tangent theta squared right here, okay, when you make that substitution. That's what it simplifies down to, tangent squared theta, right? Okay. Now we do have to get rid of the dx, okay? So let's take the derivative of x with respect to theta. So I get 2 dx d theta is equal to, and what's the derivative of tangent? Secant squared theta. Oh, now we have to solve that thing for dx, right? Well, that's not too bad, is it? So dx is what? secant squared theta, I think it's secant squared theta d theta, right? Over 2. Okay. Oh, well, that's what's going to go in here at the top. Okay. So I'm not going to try to rewrite that. At the top here, you're going to have secant squared theta times d theta over 2. So the over 2 part is that just gives me that's just going to give me a multiple of 1/2. So I can put that in front of the. I can put this 1/2 here. I can put in front of the integral. So I'm just left with secant squared theta d theta in the top. So 1/2 in front, because that's the over 2 part, and then secant squared theta d theta over this square root. Now, that square root is supposed to go away. That is the point of making the trig substitutions, is to get rid of the square root. So if the square root does not go away when you make the trig substitution, then you've missed the point, okay? But tan squared theta plus 1 is not a perfect square the way it's written, but is that one of our... Oh, yes, it is. That is secant squared theta, right? Okay, that is really secant squared theta. I think I've got that Pythagorean identity written down up here. Oh, yeah, there it is, right? So notice that if you pull the... What do you do here? Okay, notice if you pull the tan squared x over to the right-hand side, you would just get tan squared x plus 1 is secant squared. So really all of this is nice. That's just secant squared. Which is getting ready. Yeah, that's right. It's getting ready to just be secant, right? So we have secant squared theta d theta over square root of secant squared theta. But now I can extract that square root of that perfect square. So I have just 1/2 times the integral of secant squared theta d theta over secant theta. And that's going to reduce, right? To just secant theta. Ah, yeah, right. Okay, then we just figured that out a moment ago. Who had that for me? Wasn't that natural log of the absolute value of secant theta plus tangent theta? And don't forget now you get a constant what? And now, Mr. Padilla, we're going to translate that back, right? Because we cannot leave it in terms of theta, okay? So what do I have to do to get it back? Yeah, I have to convert that's right, I have to convert the thetas back into x's, right? So that's where I have to draw the right triangle. Yeah, so the right triangle is really going to be essential here. So let's see if we can draw this right triangle. So well, I can draw the right triangle, right? But I've got to just label it properly. So I have what? One angle here is theta, and this is what's going to help you. You know that tangent of theta was equal to 2x. Look back at this line. Tangent of theta is equal to 2x, right? So how can you label sides in here to get 2x as tangent of theta? That's what? Opposite over adjacent? Opposite over adjacent? 1. So now you don't know the hypotenuse, But remember, that is this squared plus this squared, right? The square root of that. Oh, look what that turns out to be. That turns out to be exactly what you substituted for, right? That's always going to be the case. Okay, that's the whole point of the substitution. So that unlabeled side is going to be that square root that you were trying to get rid of. Okay. Now you can use that, though, to figure out what the secant, well, we already know what the tangent was, right? What was the tangent? 2x, okay? So you know that tangent is 2x. So this is 2x, and we just have to know what secant is. So secant is, let's see, that's the inverse of the cosine, isn't it? And cosine is hypotenuse, so secant is hypotenuse over adjacent. Oh, how nice. So it's just this over 1. So it's just this. So it's just square root of 4x squared plus 1 plus 2x. There you have it. Forgot what we were integrating. That usually is the case, right? All of this is the antiderivative of that. Neat, okay? So there is the antiderivative of, so 1 over square root of 4x squared plus 1, its antiderivative involves a natural log. All of this. Okay, look, I got to tell you now that in the homework problems, they're not always going to simplify as neatly as this. All right, so you have to be prepared for that. And sometimes you're going to run across. In the homework problems, you're going to make the substitutions. You're going to simplify as much as possible, and then you're going to come up with what appears to be really just an impossible integral. Okay, it's probably not. But it's going to seem like it's equally challenging as the original problem. Once you've made the substitution and you have simplified, okay, so you've got to get rid of the square root. Once you've made the substitution and gotten rid of the square root, if you've really just reached an impasse, then you can try integrating this using Wolfram alpha. Okay, try integrating using Wolfram alpha. And the command is just integrate. So integrate, and then type in whatever the integrand is, and see what Wolfram alpha tells you is the integral. Okay, if it's one that you just don't see how to move forward after you've made the trig substitution. This one is not that bad, right? You should know how to integrate secant. Okay, but if you don't, then try using Wolfram alpha. Okay. Be careful now, because it's not easy to type in theta off of the keyboard, right? Okay. Not easy to type in theta off the keyboard. So you're going to want to use x in place of theta. That's fine, but this x and that will not be the same. Okay. X. So you have to watch. Be careful of that also. All right. Now we have time for another one. Okay. All right, so I'm going to let y'all try this one. First things first, how am I going to rewrite this? Because to use trig substitution, you want to have a square root, right? Right. So write this as the square root of x squared plus 1, but don't put the cube underneath. Put the cube outside, okay? So it would also be the same if you had square root of all of this underneath the radical cubed, but put the cube outside of the radical, because you want to get a square root like this, all right, that you can get rid of, okay? So that's step number 1. And now what's the substitution going to be? Yeah, u is just going to be x, sure. And a is just going to be what? 1, right, okay. A is just going to be 1. So what would your basic substitution be? And remember, x is just u. So x squared plus 1. What was the... That's tangent, right. It's a times tangent of theta there, okay? All right, so try that and see if you can get that to simplify into something that you can work from. Wow, looks hard. I'm going to cheat here and see what the answer is. Oh, God, no, it's so easy. All right, never mind. It's super easy. It's a good one for y'all to work. They won't all be this easy on the homework. I'm sorry to say that, but it's true. Y'all will, well, no, I think we already said what we're gonna substitute there. Right. Mm-hmm.
I get confused when I go here.
Mm-hmm.
So I already substitute this, right?
So you got this derivative right.
Mm-hmm.
So what's in the bottom now?
So we have to substitute it, right? So it will be tangent theta
Yeah.
plus
Mm-hmm.
1.
Square root of that. Tangent squared
Tangent
plus 1.
squared plus
Right.
1.
Yeah. Yeah. So write that down.
Okay, so it's tangent plus 1.
Square root. Square root of that, right? Because it's all under the square root. And then all of that is cubed. Don't forget the cube there.
Okay.
So all of that is cubed.
Okay,
Yeah.
okay.
Now, but here's where you make your here's where you use your Pythagorean identity, because what is tan squared theta plus 1? Yeah, it's secant squared theta, right? Okay. That's the whole point of that that substitution.
So should I just?
Yeah, what's 1 over secant theta? The secant theta is the reciprocal of what?
Of cosine.
Yeah, so the reciprocal of secant is
Cosine.
yeah, right.
I was wondering if I got to this part correctly.
Yeah, but what is u?
This.
Yeah. So put that in right there, right? Okay. That will make it much easier now.
Confused on the switchback part. Now that I know
But that's good. You got there. So now draw your right triangle. So put theta in there.
okay,
Right, theta's right there. Now remember, originally you had
my
theta. What was theta? X was tangent of theta, right? Because a is 1.
Mm-hmm.
So x is tangent of theta. So how do you find tangent of theta?
Tangent
It's
is
opposite over adjacent. So tangent of theta is x over 1.
Over adjacent, which is x over 1.
So
I
write
wanna
that in
find
that
the
picture,
sine.
right? So opposite, you'll put x, and that one you'll put 1. So what's the hypotenuse then in that picture?
I want it to turn out to be
That's exactly what it is, because no, you want it to turn out to be this, but that's what it's going to be, right? Because x squared plus 1 squared is this squared, so this is the square root of x squared plus 1 squared. This, right?
yes.
So,
Okay,
so now you can figure out what the sine
This
is.
okay. So negative sine is the opposite over hypotenuse.
Yeah, perfect. There it is.
Thank you.
Yeah, done. Hung up somewhere?
Yes.
Drawing the triangle?
Yes.
No, you're not, because what do you know about x was, so tangent of theta is x.
Yes.
X is the same as x over 1. So put that in that picture. Opposite is x, right? And adjacent is 1. Perfect. Now, what's that? That's actually going to turn out to be this. There you go, right. Now you can, remember this is minus though. Yeah. Now you can figure out what sine of theta is from that picture. Right? Okay. Y'all are making pretty good progress. Y'all actually got it, a lot of y'all got it simplified, which is really good. All right, so now let's do it here. All right, so in the bottom here, square root of x squared plus 1, since x is tangent of theta, we're going to have square root of tangent squared theta plus 1, right? I'm just going to substitute tangent of theta for x. So that would give me tangent squared of theta, right? Now, we also have to get rid of the dx. So I will take the derivative of x with respect to theta. So dx d theta is, what is the derivative of tangent of theta? Is that secant squared? Secant squared theta. And then when you multiply both sides by d theta, you'll just get that dx is secant squared theta d theta, right? So most of you have got that written down perfectly, okay? Now, the whole point of the substitution is to get rid of the square root. So if the square root doesn't go away, we failed. But we apply our Pythagorean identity because we know that tangent squared theta plus 1 is secant squared theta, right? So really, that's just the square root of secant squared theta in the denominator, which is just secant theta. So indeed, the square root did go away as planned. Oh, this is also multiplied by 3. Yeah, cubed. But that's okay, because this is still going to reduce, right? You have secant squared over secant cubed, so you just end up with 1 over secant theta, right? And then, of course, you've got the d theta. You can leave that written on the top or write it off to the side here. And now you just have to remember things about your, again, very basic trig identities. Secant is the reciprocal of the cosine. So that means the reciprocal of the secant will be the cosine again, right? Okay. The reciprocal of the cosine is the cosine, right? No, Daniel. Okay. This is 1 over cosine, right? So when you have 1 over cosine, you just get back with what? Cosine. So you end up here with the integral of cosine of theta d theta. And that's so easy to integrate, right? That is minus, don't just write sine theta there, that's minus sine theta plus a constant. So it really comes out quite simple in terms of theta, but now we have to undo the substitution. So that's where I have to go all the way back up here and remember how I arrived at theta, correct? So let's draw our right triangle. Here's theta. And all we really know about theta is tangent of theta is x. You can also express that as tangent of theta is x over 1. If that a were not 1, then tangent of theta would be x over a, right? But since a is 1, you just reduces to x. But nevertheless, tangent of theta is x over 1. So that's opposite in this triangle, right, over adjacent. So I will label the opposite as x and the adjacent as 1. And then all I need to know is the hypotenuse. But that's going to be the square root of the sums of the squares, right? So that's the square root of x squared plus 1 squared. It's exactly the substitution I made, right? Well, it was exactly the square root that I was trying to get rid of when I made the substitution. That's the whole point of the substitution. So there is the hypotenuse, and so now I know what the sine is, right? That is the what is that? Opposite over hypotenuse, right? So I have x over square root of x squared plus 1. There it is. That's the antiderivative. Oh, it is, isn't it? Right. Did I do that wrong? Yeah, I'm always so gun-shy about that minus sign, because the integral of sine is minus the cosine, okay? So I told y'all incorrect for some of y'all. Just fix that sign. Well, that's nicer. All right, so we don't have to worry about the minus sign. X over the square root of x squared plus 1. There's the antiderivative. What was the original integral? Not sure I would have guessed that. Oh, I certainly wouldn't. Okay. Well, we had to get at that in a roundabout way, right? Okay, but we found it. Okay. So that really doesn't involve our this trig substitution really doesn't involve our knowledge of how derivatives are found to find this antiderivative. This antiderivative we find in a really novel way. Okay. Applying a little bit our knowledge of trig, right? Okay. All right. Well, I'm going to leave this example off, but this is a definite integral, and that's a definite integral, right? So if we get a chance, we'll try looking at this one next time. Okay. So start working on your finish your integration by parts. Finish your integration by parts homework. And if you haven't done that already, and then start working on your trig substitution. And again, don't be shy about using Wolfram Alpha. So I hope you'll have some questions for me next time so we can look at Wolfram Alpha in class using that. Again, the basic command is integrate, but typing in the integrands is not always easy in Wolfram Alpha. Okay.